Okay, section 6.1 is for finite math. This will be the last chapter we do. I think this, as far as difficulty, this would go back to about the same kind of stuff you did last chapter. Last chapter, we talked about uh, being able to count like big numbers and using permutations, combinations, and the fundamental counting principle, and some factorials, things like that. And then we're going to apply that to this next chapter, which gets into probability. And I start out with some nice, easy definitions. An experiment is any activity that you can observe the results. And we'll talk about some simple ones like flipping a coin or tossing a die, or it could be something easier, like on a test, you can observe the results of a test either by score or, if it's a true false question, it's either true or false, but you can observe and then probably write those down. That's really where statistics comes in. You take all the observable results and then you can calculate different things with that. So moving on, each possible result of an experiment is called an outcome. And the sample space is the set of all possible outcomes to an event. And an event is any subset of the sample space. Okay, and I'm going to start off, I'm going to do some things that'll kind of lead up and you'll see how everything goes in. So if I was flipping a coin, what are the different outcomes? Well, you could have heads or you could have tails. If I was rolling a die, now that's singular. So when you roll a die, like in a game, you could get a 1, a 2, a 3, a 4, a 5, or a 6. If I was shooting free throws, you're either going to hit the free throw or you're going to miss the free throw. And let's say you're testing a spark plug, you're working out in the garage. It either works or it's defective. Works or defective. Now, it really doesn't matter how you put things down as far as your abbreviations, but that's what I put. Now, let's go back. These were the outcomes. Now, if I take all the outcomes and make a set out of them, that's a sample space. So when I roll a die, these are all the things that are possible. So if I put them together and wrote it as a set, that set is called the sample space. And usually S equals, meaning sample space equals. So on this one, your sample space would be hit and miss. And here it would be, it either works or it's defective. Okay. Moving on. So let's go back and let's look at the whole thing here. In my example 1, and these don't necessarily follow what the book does. I did it my own way and kind of brought things along. But let's consider the definitions that we had before. And my definitions were, I'm talking about the definitions I had on the first page. So experiment, outcome, sample space, and event. Okay, so if we're tossing a single die, okay, the experiment would be simply tossing a single die. You're just describing in words what you're doing. You could say tossing, you could say rolling. Sometimes you roll a die. Some people say you toss a die. That doesn't matter, but that's your experiment. And what are the outcomes? Well, I could have 1, 2, 3, 4, 5, or 6. Those would be all the outcomes. And then the sample space would be the set whose elements are 1, 2, 3, 4, 5, 6. So there's not much difference between this and this. It's just a formality. If it's a sample space, it's actually a set. And then an event, if you remember, is any subset. So maybe I'm talking about odd numbers. And think ahead, we're going to get to probability. I might want to find the probability of getting an odd number when I roll a single die. Well, if I'm talking about the odd numbers, then my event would be like 1, 3, 5. A different event might be an even number, 2, 4, 6. Or I may just say the event of getting a 1 or a 2. All those are subsets of the sample space. We'll talk more about that when we get to probability. Okay, what's a sample space for throwing a pair of dice? Okay, well, when you roll a pair of dice, put on a different sheet here so it'll show up. I'll get rid of that one now. So when you roll a pair of dice, that means on each die, you're going to have a number. Okay, so one possibility, you could get a 1 on the first one and a 1 on the second. And then also keep in mind, you're either going to roll one and then the other, or perhaps you've got two different colors. Maybe you got a red die and a green die. So you keep them separate. So 1 on the red, 1 on the green. Or maybe you got a 1 on the red, 2 on the green. Or maybe you got a 1 on the red, 3 on the green. Maybe you got a 1 and a 4. Maybe you got a 1 and a 5. And maybe you got a 1 and a 6. Those would be all the possibilities. That would be all the possibilities of getting a 1 first. What if you got a 2 first? Well, you could have a 2 and a 1, 2 and a 2, 2 and a 3, 2 and a 4. And this would keep on going. The last one you'd have on this row would be 2 and a 6. What if you got a 3 on the first one? Well, now you got a 3 and a 1, 3 and a 2, and that would go all the way over. The last one you have here is a 3 and a 6. And of course, if you keep going down, you got a 4 and a 1, you'd have a 5 and a 1, you'd have a 6 and a 1, and these would go all the way over. And over here, you would have a 4 and a 6, 5 and a 6, and the last one would be 6 and a 6. So if you put all those together, put braces around it, that whole thing would be your sample space. How many elements are in the sample space? Well, you have 6 rows, and you have 6 columns, so that means you got 36 altogether. Something else we'll do later with this is we'll make like a table. Okay, and maybe this is the red die, and this is the green one. So on the green one, you could have a 1, a 2, a 3, a 4, a 5, and a 6. And on the red one, you can have a 1, a 2, 3, 4, 5, and then a 6. Okay, and I'm getting a little ahead of myself, but when we do this, most of the time when you play games, if you roll 2 dice, what do? You add them together. So if you got a 1 on a red and a 1 on a green, that gives you a 2. A 1 and a 2 gives you a 3. 1 and 3 gives you 4. 5, 6, 1 and 6 gives you a 7. On the second row, 2 plus 1 is 3, and then you got 4, 5, 6, 7, 8. The next row is going to go 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. And the last one, 7, 8, 9, 10, 11, 12. And when you look at these, how many sums do you have? And that's what we got here. We got sums. There's 36 entries. But when you look at it, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 11 different sums that could come up. I'm getting way ahead right now. Let's get back to the lecture. I'll come back when we start doing our problems, then I'll have that in there for you. Okay, so the sample space I did on the other paper. So that part's done. Okay, my second example. Let's say we're flipping coins. What's the sample space for flipping one coin? Well, one coin, you either get heads or tails. Okay, that was one. The next one says, what happens when you have two? Okay, now let's go back. Let's say we have a tree diagram where you got heads, tails, that's the first one. And you got heads, tails, heads, tails. So there's the second toss. So when you follow these, you got HH, that's the first outcome. The second one would be heads, tails. Next one would be tails, heads. And the last one would be tails, tails. So how many entries do you have in that sample space? Here we had two, heads and tails. When you go down here, you got 1, 2, 3, you got 4 of them, 4 outcomes. And then when you go to 3 coins, take that same tree diagram and let's extend it out one more branch. So now when you follow the branches, you got heads, heads, heads. I'm going to write it like this. Heads, heads, heads. You got heads, heads, tails. You got heads, tails, heads. You're going to have heads, tails, tails. If I start out down here, I go tails, heads, heads. Put it over here. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And the last one's going to be tails, tails, tails. So that whole thing is your sample space. And now you got 8 of them in there. Okay, here's a real life problem. I hesitate on putting it in, but perhaps you should look at it. It says number of people in a queue. I'm not sure what that means. That's a weird word for me, but when you read the problem, it looks easy. It said once every hour, a supermarket manager observes the number of people standing in a checkout line. The store has space for at most 30 customers in the line. What's the sample space? So what you're saying, that manager's going to look out and he's going to count. So what are the different numbers he could put down? Well, he could look out. If nobody's there, he's going to put a 0. Or if there's one person, or if there's 2 people, and that's going to keep on going, right? Up to 30. Because it says at most 30 customers could fit in there. Anything past 30, I guess, are outside the door. But this would be your sample space. These are different numbers, meaning how many could he count at any one time. Okay. Okay, now the next part's going to look very familiar. It's the same thing we did last chapter. We talked about union, intersection, complement, and then this one's going to be a new one. I'll talk about that in a second. But these really mean the same things. E union F. You'll notice that they use the letters here, and these stand for events, not sets, but events. But the union represents all the outcomes that are in either of the two sets or both. So as long as it's in at least one, you're okay. The intersection, same symbol, E intersect F, are those outcomes that are in both E and F at the same time. The complement would be the events of the universal set that are not in E. And mutually exclusive, all it really means is they do not intersect. Or you could say E intersect F would be the empty set. Okay. If you understood it last chapter, this will be a breeze for you. Okay, so we want to find each of these. So this is just kind of a review. E intersect F. So E's got 2, 4, 6. F's got 1, 2, and 3. What do they have in common? 2. E union F. So it could either one or both. Okay, I got a 1 over here. I've got a 2. I got a 3. Actually, all those are all in F. And when you go back to E, you pick up a 4 and a 6. So the only thing that's really missing is the 5. I don't know if you can see that, but that's the complement of E. So E is 2, 4, 6. So the complement would be all the ones not there. So that would be 1, 3, and 5. The complement of F is 1, 2, 3. So the complement would be 4, 5, 6. And then you could go back and do combinations of things. So the complement of E intersect the complement of F. So if here's complement of E, there's complement of F. What's the intersection? What do they have in common? The only thing I see is a 5. That's the only element they have in common. Okay, and then the union of these two sets here. So I'm going to have a 1. There's no 2, but I'm going to have a 3, 4, a 5, and a 6. So it's everything but the 2. Okay, and here's the last thing. Here we're going back. We're going to talk about mutually exclusive. So S is the set A, B, C, D, E, F, G. The event E has A, B, and C. F has E, F, and G is E, D, and F. We want to know whether we've got several down here, 6 of them, which ones are mutually exclusive. So let's look at E and F. What you're really saying is, do they intersect? So is there an intersection between E and F? No. That makes this, yes. They are mutually exclusive because they do not have an intersection. What about E and G? When I look at E and G, they both have a C. That makes that a no. So if there's an intersection, the answer is going to be no. If there's no intersection, the answer is yes. F and G, I see both of them have an F. So that's a no. Okay, on this one you got the complement of E and the complement of F. So let's just write those down. The complement of E will be equal to, that's A, B, C, so this would be D, E, F, and G. And the complement of F would be A, B, C, and D. So when I come down here, the complement of E and the complement of F, do they have anything in common? Yeah, they both have a D. That makes this a no. If they intersect, it's no. This says the complement of E and then G. Okay, so here's the complement of E, and there's G. Do they have anything in common? Well, I see both a D and an F. So that means they intersect. That means this is going to be a no. If they intersect, they are not mutually exclusive. Okay, and then F. Here's F. And the complement of G. I'll put the complement of G down here. So you're going to have A, B, what else is missing? E, and G. So you're looking at this one, E, F, G, and down here, I see E in both of them, I see G. So this is a no also. So the only one that was mutually exclusive is the very first one. That meant they did not intersect. Okay. That takes care of this lesson. It wasn't very hard. I didn't think it was. And hopefully you'll be able to follow through and get your work done. And see you next time.